Hello, community. Today we talk about our complex LLM here in the middle. Then we talk about retrieval model here somewhere in the periphery. We have a lot of data models with external data, internet data, corporate data, databases, vector databases, what else? And we talk about pipelines. A pipeline that is smart and that can program itself. So here we start, and at first, we have a task. We have a task for our LLM. We have a complex task. And an LLM can reduce a complex task to multiple simple single tasks. And this task nodes we call modules. And whenever we have a node in a network and a node in a graph structure that has become task specific and smart, we can here construct multiple intelligent nodes in our graph structure. So each node does only one part of the job, such as finding the relevant information, it's a retrieval node, generating a response, it's a prediction node, or refining the response of the system, it is an optimization node. And what goes between the nodes? We have edges. Edges denote the flow of data. But now, since we have intelligent nodes, we have self-programmable intelligent edges. And this is nice. So, in my last video where I explained you the state machine and the state space differences, I showed you that with LangGraph, now the development of LangChain to LangGraph, multidimensional, we have how to create a graph. We define the state of the graph. We define the agent nodes, we define the edge logic that we have, and then we put everything together and we finally define a graph. And I told you that LangGraph is here very similar to the user interface of Network X. We know we love Network X for multiple years, it's beautiful. So you see here our UX notation, add node, add node, add node, add conditional edges. And we built here our graph. And then we have a simple compile functionality here that makes our graph runnable. So very simple structure from LangGraph. Of course, we do this now in LCell and not in LangChain notation anymore. That is legacy. But today we do something much more interesting, much more intelligent, much more beautiful. We're looking here at pipelines that are self-configurable, pipelines that are self-learning, pipelines that are self-optimizing, and pipelines here that are, and you're not gonna believe it, graph-based pipeline representation in a mathematical space. And whenever we can see a pipeline connecting, for example, a language model and a retrieval model out there, as a graph structure, we have the beauty of graph theory, and we have so many tools from graph theory, and we now gonna use our tool for this problem. I have videos here, node and edge classification in graph machine learning about uncover the secrets of graph machine learning with graph datasets, or if you're more interested in the theoretical side, the Weisweiler-Lehmann test, or the topological graph layer. Of course, we go with graph Sage to graph BERT for our neural network. We program here, for example, in PyG, the torch geometric data classes for convolutional structure, or I showed you in this video how you can use PyG and our sentence transformer SBERT for using here node classification. If you're interested in the mathematics, the neural Bellman 4, the graph neural network here with link prediction AI, this is the video for you. Or if you want to go beyond graph neural network, I have here beyond message parsing methodologies. And then in a pure, more mathematical view, we go even to simplicial complexes on CW networks here that will have here the topological message passing on graph neural network if you want to have a deeper dive into the tools that we're going to use. But for Ben, hey, it's really easy. We have a central intelligence. This is our GPT-4 system. Then we have here a lot of external data, somewhere internet, corporate data, databases, vector databases. And now we want to have here intelligent, self-programmable pipelines that connect here to task-specific issues. Great. You see, why we apply here this graph-based approach? And I think 5 reasons: flexibility, modularity, optimization, scalability, and interpretability of graph structure is simple, beautiful. So here we have it. We have here our central large language model. And if you want, here on this pin wall, we have now our nodes, our edges, our information nodes can be LLMs, can be databases, can be parts of the internet, can be mathematical simulations, whatever you can think of. And you want that this system is self-training, self-optimization, and is performing here to the best possible means. We need a compiler function, as I showed you in langgraph, but now we want some automatic compiler optimization where a compiler takes the training data, the interconnected modules, our nodes, and our defined performance metric. The simplest metric you can think of is accuracy. And then you want that the system starts to self-optimize the whole pipeline. This means it chooses the best configuration of node edges and everything else, and the optimal parameter of our subsystem that are connected with this intelligent pipeline. And yes, the compiler will be beautiful, and I know that you are looking forward to this, but you might say, hey, wait a second. Didn't you not forget something? And you're right. Context. I have not given you the context if you are younger or just starting here with this. So, where did it all begin? In January 2023, exactly 1 year ago, Stanford University. It built something, a demonstrate, search, predict idea to compose retrieval and large language models for some knowledge-intensive NLP tasks. And here we find it again. So we have here frozen language models. So we do not fine-tune them. They have their fixed weight tensors. So we're going to use in-context learning. Now, on the other side of the pipeline, we have our retrieval models, our expert systems, our databases, our vector store, whatever you have out there in the world. And they say, hey, our vanilla language model functionality did not work. Our retrieve and read functionality is not really good. So we are developing something like a multi-hop DSP program that finds here the solution. So 1 year ago, we started with in-context learning, adapts a frozen language model to tasks by conditioning the language model on a textual prompt, including task instruction, few short examples, and a few demonstrating examples. This is what we today would call here a simplified RAG system. And exactly 1 year ago, this is how easy it was. You had the demonstrate phase, you had the search phase, and you had here the predict phase. So you had your complex question here. And then you have given, 2 short examples here in context learning. You trained here, training, as an in-context learning training. You trained here the model, you told you, hey, this is the way I want that you answer to my questions. But the nice thing is that this system was able here for the demos, for the demonstration data, that they could go from one hop to multi-hop. So the system would have a complex question, find here in its in-context learning how to create 3 simple questions out of a sequence of questions out of this complex question, and then just answer in hop 1, hop 2, hop 3 here till it found here the correct answer. And with this, it was able to predict here for every complex question that was similar here the right answer. So we have retrieval augmented in context learning for a frozen language model and a retrieval model 1 year ago. Beautiful. Now, this DSP program was relatively simple. Stanford really focused here on simplicity. So here you have in your multi-hop program, yes, you can read it yourself. And it included examples of the desired behavior from the language model in its prompt, in context learning. And this leads to a better performance. So in DSP, we call this additional training data demonstration. A demonstration is a training example that has been specifically prepared to illustrate here our specific desired behaviors from our large language model. And of course, we have a training example, so we have also a transformation, a mathematical function that takes the input x of a specific type and prepares here a list of demonstration, typically by selecting a subset of the training example and bootstrapping new fields in them. This is here the most important sentence here, bootstrapping new data structures or bootstrapping demonstration examples. So you see here the program, very easy, but I just wanted you to understand the main idea. So the demonstrate stage here, the very first stage from DSP, can augment a training example by programmatically bootstrapping annotations for intermediate transformation. So this means today we will say, hey, we generate some syntactic data. In our running multi-hop example, we have 3 LLM-based transformation that's going to happen. LLM-induced based transformation. At first, how to break down the input question in order to gather information for answering it. So, one complex question, a sequence of 3 easy-to-answer questions. Much easier for the system. How to use information gathered in an earlier hop to ask follow-up question, and how to use this information gathered to answer the now in total all the primary complex question. Easy, I know. But this syntactic self-generated DSP data are now the nucleus here of this powerful system. This DSP ability to self-generate new demonstration example was at the time really something beautiful and we will build upon. So this feature leverages here the language model generative abilities to create additional syntactic training data on the fly. But on the fly means also within the knowledge domain that we need to answer the task, to answer our main query. So this process now, somehow even with rigid templates, enabled our DSP system 1 year ago to continuously learn and adapt, improving its accuracy and efficiency over time. And now you understand, if I tell you all this boring stuff, what happened a year ago, and it could, at a year ago, continuously learn and adapt if we use here some rigid templates, you now understand where I'm going with this. If I tell you that 1 year later, we have self-programmable and self-optimization modules in a graph structure. And yes, it took almost a year for Stanford to come up with the solution. Okay? So we have now more data, more specific queries. Yes, beautiful. So just a summary. What is DSP? Demonstrate, search, and predict. 3 phases. Let's summarize again. Demonstrate. The language model is primed with some few short examples that illustrate the desired task outcome, leveraging in-context learning. We do not fine-tune the LLM. We have just in-context learning within here the context length of our prompt to adapt the model to a specific task without the need for retraining, fine-tuning, or whatever. This phase sets the foundation to providing the language model with a conceptual understanding of the task at hand in our specific chosen domain, enabling it to generate some queries for the retrieval model and to interpret the retrieved information within the domain knowledge that the LLM has been pre-trained and fine-tuned on accurately. Beautiful, easy. Search, even easier. The retrieval model comes now into play, utilizing the capability to sift through the vast corpus of information to find data relevant to the queries generated by the language model, crucial gathering pieces of information necessary to construct a coherent and accurate response of the initial query, and the sophistication of the DSP framework allows for multi-hop searches where the outcome of an initial search informs subsequent queries, enabling the system to navigate through layers of information similar to human reasoning. And here we see already shining through what is unique. The more the system finds new data, the more the system finds subqueries that it can answer, it can enhance its own new knowledge domain. And then with predict, you notice predict phase sees the LLM synthesizing the data also from the retrieved information into a comprehensive response. And this is where the DSP framework really shines, as it employs here the language model intelligence not only to generate an answer, but also to articulate a chain of thoughts that outlines the reasoning behind those answers. Today we know this is classical, but a year ago it was really nice. And the author said, hey, this is instrumental in creating transparent and explainable AI system, as it provides insight into how the LLM arrives at its conclusion. Great. Now, they run some real tests. So they say, hey, for the search phase, let's say we have an open domain query and answer. Our program uses the question directly for retrieving 7 passages. And those 7 passages are concatenated into our question and answer prompt with a chain of thought. And then in the predict phase, this generated 20, or they let 20 reasoning chains to be generated by the LLM, and uses here the self-consistency to select its final prediction. So 20 reasoning chain and find out which is the best one. And you already see where we could go with a programmable model here a year later. And then in the demonstrate phase, they said here, k equals 3. So annotate requests annotating only 3 demonstration hour additional training data, which will be used in the prompts. Beautiful. Here the pseudocode for you. Template, yes, we had rigid templates, but already templates that had here this interesting nucleus in itself. Innovative approach at the time designed to enhance the capabilities of frozen LLMs and retrieval models by enabling them to work in concert to tackle more complex, more knowledge-intensive tasks. And now Stanford had almost a year to develop this methodology to make it programmable. Here we have a simple example. The task, let's say, the complex task is determine of the influence of Newton's law on modern space exploration. So, first step, the initial query formulation. Understand here, the language model comes in and says, hey, what are the key components that I need to understand? Newton's law and application in space. And if it's an intelligent model, it checks if it has this knowledge domain in its pre-training data and its fine-tuning data, and if also it has access to some retrieval models, to some databases on the internet about space exploration, the NASA database, so that this particular knowledge domain is also available for the retrieval model. So if it has the intelligence on this domain and it has access to additional data in this domain, the system starts to work. Then we have now the retrieval model searches. So whatever is the search, it's a keyword search, or if it's a semantic search with a cosine similarity in a vector space, you just gather additional information and you create a demonstration data set. So let me show you hop 1 here by the retrieval model. Now the input is easy. So we have part 1, Newton's law, part 2, space exploration. So let's do this. The input is what are Newton's law of motion, and the output is what it found in the retrieving the data and the information. Retrieves a summary of Newton's 3 laws of motion, emphasizing their principle of inertia, acceleration, force, and reaction principle. Second was space exploration, how Newton's law applied in space exploration, and then our retrieval model. Our RAG system finds information on how Newton's law have been fundamental in planning space mission, in including here orbit calculation in the flight path, in the complete spacecraft designed for re-entry, and in the complete navigational task. Beautiful. Step 3 is then using this information from the retrieval state. The language model synthesizes here a complex demonstration that outlines how to connect historical scientific principle, Newton's law, with modern application in the space. This is step 3. So our language model says, create a demonstration example that explains here the influence of Newton's law on modern space exploration using now the retrieved information I just showed you. And the language model output is now, this is the new synthetic data set that we generated here. So the question is, what is the influence of Newton's law on modern space exploration? And now the answer by our language model is, Newton's law of motion have had a profound influence on modern space exploration. They are fundamental to understand and predict the behavior of spacecraft in the vacuum of space. And we get also a reasoning path by our LLM. And here the reasoning path is now here also the beauty, because it gives us here some pathways, some new data sets, some new wording, some new information, new clues that how it is connected to other parts of the knowledge domain. The answer is Newton's first law, the principle of inertia, helps in designing the spacecraft that can maintain motion in space without continuous propulsion. The second Newton law provides the basis for calculating the force needed for a spacecraft to escape Earth's gravity. And the third law explains the principle behind rocket propulsion. Yes, this is rocket science, where the expelling gas out of a rocket engine produces a thrust needed to propel the spacecraft forward. All of this is crucial for mission planning, for all launch calculations, for maneuvering in space, and for landing our spacecraft on other celestial bodies. So you see, from a simple question with this DSP methodology, we can get cleverer and cleverer every step on the way. Step 4, talking about steps, application in future queries. This detailed demonstration includes a multi-step reasoning path, what I just showed you, that connects theoretical physics, yip, hooray, with practical engineering. Okay, yeah, you have to do this. Can now guide the DSP system in answering related questions. It serves as a model for how to construct reasoned answers a year ago that require integrating historical developments with their contemporary application. And step 5, it goes on and on and on. You have continuous improvement and expansion, and this is beautiful. So you have now, based on some rigid templates and some rigid coding that humans have done, an ongoing learning process that enhances the system's knowledge base and its reasoning capabilities. And now you know, if a year ago we have rigid templates and rigid code and everything else, now you know that this is the context we need to understand what happened a year later when Stanford University came back and showed us programmable interfaces and programmable pipelines. So this example, what it does, it demonstrates the DSP, the old, not 2023 framework's advanced capabilities to self-generate demonstration synthetic training data for complex multi-hop questions to improve our in-context learning. So no fine-tuning of our LLM, but an optimization based on the external data available. And in January 23, they called this retrieval augmented in-context learning. So not retrieval augmented generation, RAG, but retrieval augmented in-context learning, or AICL. I was just interested, so I searched here on GitHub the LangChain AI, and I found it because there's an issue where I say, hey, demonstrate, search, predict. Exactly here, this piece of knowledge from Stanford University. And you see, just days later, there was somebody says, hey, it looks like we could incorporate this into our LangChain functionality. And some other people came and said, yeah, even in March, they said, hey, interesting. Any thoughts on this? And then half a year passed, and then the bot from LangChain came back and said, hey, I'm your bot. I just noticed that there's the issue titled Demonstrate, Search, Predict. Okay, it's great to see some positive feedback. Before we proceed, we would like to confirm if this issue is still relevant to LangChain. And then the bot closed the discussion. Okay, of course, Stanford continued with its investigation. It's developed DSP much more advanced version in Python, of course. You see here the Python compiler. So DSP consists, 2023, of a number of simple composable functions for implementing in-context learning systems as programs instead of and task prompts like LangChain or LangGraph for solving new knowledge-intensive tasks. They implemented this. You see, 2023, you just used GPT-3 as an LLM. But of course, they heavily invested in this. And now I can show you the new self-learning DSP system. And here we have it from Stanford University, UC Berkeley, Carnegie Mellon University, Amazon, Microsoft. Beautiful. Compiling declarative language model calls into self-improving pipelines. So here we are exactly self-improving pipelines between language model and retrieval model, where we have an intelligence, an artificial intelligence, and now we use this to optimize here our pipeline structure. We are not based on rigid templates or rigid something, but now we have a self-learning system and we have a beautiful compiler. And I know you are waiting here for the compiler, and of course we will do this. But unfortunately, as Google, YouTube told me, my videos are only watched 10 minutes on average. So therefore, this is the end of part 1. It would be great to see you in part 2 of this video.